Today we're going to start section 3.4, which is addition and subtraction algorithms. I know it says and mental estimation, but we won't get to that part today. We talked when we were doing sections 3.2 and 3.3 about the fact that there's kind of two components to basic math facts. One of them is the understanding why things work, and that's what sections 3.2 and 3.3 did. Focused big time on why in the world when we do this multiplication it looks like repeated addition, or why in the world these sort of things actually work, okay? These two sections, 3.4 and 3.5, are going to be focused on doing things efficiently, quickly, correctly. So not just efficiently, but also effectively. And there's going to be places where you're probably going to be like, that was the dumbest method for doing something, and I absolutely think that that's ridiculous. There's probably going to be some of those. And that's okay, but what you need to understand is that it's really not about you. It's not about me either. It's about being able to give a student who does not like or does not seem to be able to grasp the method that you really love and want to teach another way to do it. Okay? So try to keep that in mind as you're looking through these, and you're probably looking down your nose at some of them going, how dumb is that? That some kid somewhere is going to just think that you are the best person ever, and their parents will think so too because you gave them a method that worked for them. Okay? Everybody good with that? Okay. So we're going to start with the concrete model. You have seen this one used. This is usually where you would start. And we are starting with addition, by the way. So the concrete model actually has to do with looking at those base 10 blocks that I brought that last time. Remember those red base 10 blocks? Okay. So when we're looking at the 34 and we're thinking about it from a concrete model perspective, we're thinking in terms of longs and units because I only have two-digit numbers here. So 34 would be 3 longs and it would be 4 units. Okay, so we have sort of this one grouping of things. It's kind of running into my question. Maybe I'll move that down a little bit. And we're, if you will, adding to that another group. And the other group will have in it how many longs? 1 long. And how many units? 8 units. And what this method really does well is it gives visualization to the idea of regrouping, because you physically can take those individual units and connect them together, especially if you had the manipulatives themselves, connect them together to show that if I take 10 units, it will become a long. So I'm going to group together all 8 of these, for example, and 2 more of these. And these 2 grouped together become 1 long. I already had 4 longs. So now I have how many longs?
5.
All right, we're going to do this. Hang on a second. Okay, so there's my 3 longs. They're a little bit bigger now because I just changed my size of something, but you get the idea. Here are my 5 longs that apparently I can't draw parallel to the ones before or whatever. And then how many individual units do I have left? 2 that I didn't regroup with. And a very quick count of what I have allows me to see that this is, 52. Another nice thing that this does is it actually shows why it doesn't make sense to count these up and say the answer 7. Because the different sizes of things, right? I can only count and group together things that are of the same size. So there's 6, there's not 7, things I'm counting. There are 5 of the same size, 5 longs, and 2 units that are there. So this is a concrete model. The standard algorithm is probably the one that you know and love, or at least the one that you use all the time because it was the one that was probably maybe even the only one taught to you when you were younger. And it is still being taught, so I don't want you to think like that they threw this out the window. They didn't. But just as a reminder of how that works, you have 34 and you have 18. And as we work our way through this, I'm going to point out some things that you probably haven't thought of or maybe haven't thought of in a long time as to why this process can be difficult for kids, especially when they're first learning it. The first difficulty is what numbers do you add together first? The ones on the right-hand side. Any idea why that might be counterintuitive? We read from left to right and we're doing math from right to left, and that's a little bit strange. Truly, it's a little bit strange. Okay, so already right off the top we've got something weird going on because the order in which we're doing it does not match the order in which we do practically everything else. Now, when we add those together, we get 4 and 8, and that's the number 12. And so we do this really weird thing where we write down a 2 and we carry a 1. And oftentimes, while the kids might even be able to do it, they don't know why they're doing it. So do you know why I put a 1 into the next column? Because I made a group of 10. That's the real reason why. I regrouped. So even the papers that my second grader comes home with right now, and they'll use the phrase regrouping, which is amazing, and I'm so glad. But my husband looks at it and he's like, I don't know what they're talking about. Because the language that we're familiar with is carrying, not regrouping. So he sees that, and you may even still, when you're teaching, have parents see that and go, I don't know what they're talking about. They're using words that weren't the words that I used when I was a kid. Okay? So what they're really doing is regrouping, and they're carrying the 1 because they have regrouped it to be 110. And then, of course, we add the 1, the 3, the 1 together, and we get a 5. Now, in terms of efficiency, this is super efficient, right? I don't have a big old picture. I've got this nice little tiny diagram. It's super efficient. But in terms of processing through it the first time, or maybe even the first several times, the idea of starting on the left, or the right instead of the left is confusing, and the idea of doing this weird carrying thing is a little bit confusing as well. When paired alongside of the concrete model, you can understand better why this regrouping does put a 1 in the other column. Because this visual over here did the same thing, didn't it? I regrouped 10 of those 1s together when I got 12, and I turned it into a long, and then I grouped it with the longs. Okay? Now, the next one is much like the one we just did. It's called the expanded algorithm, and it's kind of a mix between the standard algorithm and the concrete model. So let me show you how it looks. And there are some variations of this, but the basic idea is to take the number 34 and to write it as 30 plus 4, and to take the number 18, and write it as 10 plus 8. So you're isolating the value's place that it's in. For instance, the 3 is not really a 3, it's 30, right? So there's a reason that that 30 has a 3 in the place it does. 3 10s is different than 3 1s. Now, the nice thing about this is you can add from left to right or right to left, because this isn't your final step. The bad thing about it is this isn't your final step, which means that it's a longer process. There's a trade-off. So if I in fact move from left to right, I get 40 here and I get 12 here, correct? All right, so if I have 40 and I have 12, I can do the same thing with the 12 that I did with the original 18 and so forth, is I can break it apart into its 2 components. So I can write this down as 40 plus 10 plus 2. And again, the 40 and the 10 are components that match, so they become 50, and I have the 2 for 52. I'm going to show you one other variety of this too. This is one variety of how to write expanded form. Another variety of how to write expanded form is to recognize that I have 34 as 3 times 10 plus 4 times 1. So truly writing out like legit expanded form, like times the base that it's in. Okay? And I have 1 times 10 plus 8 times 1. Now I can still add the same way that I did before. The things that are times 10 can be added, so this is 4 times 10. The things that are times 1 can be added, this is 12 times 1. And I can, again, go through the same process where I say 4 times 10 plus 10 times 1, or 1 times 10, that's what I meant to write. 1 times 10 plus 2 times 1, I'm breaking apart the 12, and then these two are quote-unquote alike, which gives me 5 times 10 and 2 times 1, or 52. So would I encourage your students to do this on a regular basis? Well, no, because it's cumbersome in terms of what you wrote down. But if they're having trouble understanding why that's working with the standard algorithm, it might be a good in-between step to show it. I'm a bigger fan of what I did on the left than what I did on the right. And the reason is because you usually teach addition before you get to multiplication. And you usually teach 2-digit addition before you get there as well. So the idea that you're employing your multiplication in the middle of this when the kids might not have even covered it before starts to feel a little bit counter-helpful, right? It's just not, it's not useful to me at all. So I like the one that's on the left better, but you do see both versions of them, okay? And of course, they go along with our units, right? I mean, they go along with that concrete model. It's all the same stuff. It's just a different representation for it. All right, I'm going to show you the next one, which is legitimately called the left to right algorithm. And I've created numbers that are a little bit bigger just to show it out a little bit better. That's the only idea. So you could use this algorithm with the 2 numbers we did before. It wouldn't be a problem, but it's more fun with more numbers so that you can see how it's really working. Okay, so we're going to write it in sort of a vertical format like I wrote the other ones too. So 1,534, 3,218. And what we're going to do is we're going to add from left to right. So I do need to understand that when I am adding the 1 and I'm adding the 3, whether I write it or whether it just in my mind I know it, this is 1,000 plus 3,000. Okay? That's really what I'm adding. And 1,000 plus 3,000 is 4,000. So the first thing I do is I write down 4,000. The next step adds a 5 and a 2, but the 5's not really 5, it's 500, and the 2's not really 2, it's 200. And 500 plus 200 is 700. So I write down 700. And then I have a 3 and a 1, but it's not really 3, it's 30, and it's not really 1, it's 10. So the 30 and the 10 become 40. And this just to show you what happens when the number's too big or bigger than what you would have had. I've got that 4 and the 8 on the end there again, and 4 plus 8 is 12. And so it's okay that I'm taking up 2 places. It's not directly underneath the 1's unit because I have a tens place anyway, so I just put it into the tens place. And then most of the locations have lots of zeros in just one number. So there's not a lot of addition to be had at the very end. And for the most part, you can still move left to right. So this is 4,752. Okay. Again, it isolates place value. That's helpful. This one moves left to right, which is helpful. But the cumbersome part is there's more writing. There's more steps to it. Okay, this one's an interesting one. It's called the Lattice algorithm. So what we're going to do is we're going to write down, just like we did before, the two numbers, 1,894, 3,218. And what I want you to draw underneath them is a, if you will, a long box that you divide into 4 columns. So the columns go underneath the place values, is your basic idea. So if this had been a 5-digit number, you would be creating, okay, I can't get it to be straight, so I'm just going to have to freehand. If this were a 5-digit number, you'd be creating a 5-digit box. Okay, so it's the number of boxes is the number of digits in your problem that you're adding. And then you're going to create it into a lattice. What that means is you're going to divide each of your boxes along a diagonal. Bottom left, top right. The diagonals do need to be in the right arrangement. You can't just draw any diagonal you want. Bottom left, top right. Okay, everybody good so far? Okay. We are going to add, and you can go left to right or right to left, doesn't make any difference here. We're going to add the columns together. So I'll go from left to right, since I've already told you that's a point of concern sometimes for kids, is that we always move in mathematics sort of backwards. So if I do 1 plus 3, I get the number 4. And what you do is you put the single digit in the lower box. And then notice when I get 8 plus 2, I have 10. Well, when I have 10, the 1 goes in the top box and the 0 goes in the bottom box. So 2-digit numbers, larger value goes on top, smaller value goes on bottom. 9 and 1 is another 10, so the 1 goes on top, the 0 goes on bottom. 4 and 8 is 12, so the number 1 goes on top, the number 2 goes on bottom. Okay, everybody good so far? Okay, what I'd like for you to do next is to extend your lattice diagonals down. Just extend them lower. This one, unfortunately, on this step does matter in general. It may not matter on this specific problem. In fact, it doesn't. But in general, it does matter that we go back to going right to left. So that might be a reason for you to be like, not going to go left to right to start with and then switch right to left. You do have to go right to left on the bottom step. So the bottom right-hand corner has a 2 in it. We're going to write down a 2. And then what happens next is along this diagonal here, I'm making it really big and bold so you can see what I'm talking about, we add any numbers that are along that diagonal. So in this case, it's a 1 and a 0, and we get a 1, of course. You go along the next diagonal, it's another 1 and 0, so you get a 1. And along the next diagonal, it's a 1 and a 40, and you get a 5. This is more compact than the other methods we did, right? It's condensed. That part's really nice. I do have a little bit of visual appeal for your visual learners. They've got this box, and that's kind of geometric and fun, but it's more compact, okay, than some of the other methods. Are we good with this one? There's one more method. This method is, I want you to write this down, your own handwriting right beside this. This is good when you have many numbers to add. It's not about the size of the number, it's about numerous numbers to add. So you'll notice I have 4 numbers I'm adding here and not 2. It's just kind of useless if you only have a couple of numbers you're adding together. But when you have a long list of numbers you're adding together, this is useful. I'm a super big fan of scratch addition when there is multiple numbers to add. Okay? So let me show you how it works, and I'll probably have to show you twice. So can you guys just watch me the first step? Don't write anything down, and then I promise we'll go back and I'll explain it again while you write. Okay, so just watch for the first step. We're going to write it down just like we were on the other one. So you shouldn't be writing right now, right? Everybody's just watching? Okay, so the reason that this problem would be difficult for students is because at some point you're adding together very large numbers, or at least larger than single digits. Agreed? So in the first step, if I add on the right-hand side, we're going to go right to left like we normally do our math, okay? 4 plus 8, just top to bottom. 4 plus 8 is 12. That's usually okay at the point when kids get here because they know their digits that are ones digits, 4 plus 8. 12 plus 9, they may not know off the top of their head because they probably, not always, but probably didn't remember or memorize 12 plus numbers. That's not always the case. Sometimes people do memorize up to 12, but they don't go up to 13, and then we're going to have the same argument, right? Nobody memorizes 13 plus 7 and 13 plus 9 and 13 plus 4. It's just not a set of tables that you memorize. So what we do is once we exceed the one-digit number, we're going to slash it out. So 4 plus 8 is 12, which is more than 10. Agreed? How many more than 10? 2. So I make a scratch mark and I only remember the 2. And I take that 2 and I add it to 9. Again, that's single digit addition. 2 plus 9 is 11, which is more than 10. So I scratch again. How many more than 10? 1. 1 plus 7 is 8. And I'm going to write my 8 down. And then I count up the scratches, and there were 2 of them. And so then I regroup, I carry the 2 to the next column, and I do it again. 2 plus 3 is 5. That's fine. 5 plus 1 is 6. That's fine. 6 plus 6 is 12. That's too many. How many too many? 2. 2 plus 8 is 10. That's also too many. How many too many? 0. I mean, if I take away 10, there's none left. No left. It's a 0 left over. That's what we have, right? Take away 10. How many scratches? 2. So and since I carry a 2, there's nothing in the hundreds column, so this 2 just ends up being carried down to the bottom. Okay? What it does is it eliminates the need to remember a larger number. You only have to remember the ones digit every time you do it. And that's very friendly because everybody, when they're learning these digits, learns the 1 plus 1's table. And I don't mean the number 1, but I mean single digits. Okay, so let's go through it again together. You can write things down this time as we're working through, and we'll go through it again just like I did, so you've heard it twice. So we're going to write 34, 18, 69, and 87. So the whole idea of this algorithm is to use it when you have lots of numbers you're adding together. And really, when I'm saying lots, I mean more than 2. I mean, 3 is not a lot more, but it would work okay for that. More than 2 together. And when you are adding numbers in some sense that you want to avoid getting these numbers to being large. Okay, you want to make it simpler to do the addition. So what we do is we go from the top down, just like always, on the right-hand column. 4 plus 8 is 12. And anytime that number, when you add it together, is more than 10, you scratch. So 12 is more than 10, so I scratched. And scratching is equivalently saying, I'm going to ignore the 1 in the number 12, and I'm only going to remember the 2, the units digit. 2 plus 9 is 11, and that's more than 10, so I'm going to scratch. I know I'm saying more than 10. It's at least 10. I should say it that way. It's 10 or more. I'm going to scratch, and how many more than 10 is it? 1, and then I add the 1 to the 8 or 7 that I have, and I get an 8. And then I count up the scratches because when I scratched, what I did is I removed 10 every time from the number I was remembering. So I removed 10 twice. That's 20. So when I count my scratches, I end up with a 2. Okay, 10's column now. 2 plus 3 is 5, plus 1 is 6, plus 6 is 12. And we just keep going until we get something bigger than a single digit number. So bigger than 9. So we got 12, so that's 2 bigger than 10, yeah? And then 2 plus 8 is 10, so we scratch again because it's bigger than a one-digit number. And it's exactly 0, too big, but I scratched because I got to 10. When I scratched, I count up the or when I'm done, I count up the scratches. There are 2 of them. So this gives me a 2 here. Okay, are we good with that? All right, let me see where we are in terms of the numbers of pages left. Okay, because we have the mental estimation at the end, let's at least try to get our subtraction algorithms done. Okay, subtraction algorithms, some of them, in fact, a lot of them are going to feel like, didn't we just do that with addition? And the answer is going to be yes, we did. The first one's called the concrete model. We did that with addition. What did the concrete model look like, or what did it mean we were doing? We're drawing pictures, right? And again, if you were doing this in the classroom, you don't have to draw the pictures. You could actually have manipulatives sitting there that you're using to do the problem, right? That's the equivalent. So this is sort of my pictorial equivalent of having blocks sitting in front of children. So this model, actually, instead of adding them, is going to subtract them. I have 34, so here's 3 longs. And I have 4 units. And it tells me from this group of objects, I want to remove 18. And there's a problem with that. What's the problem with removing 18 from this picture? I don't have 8 units. Does everybody see that okay? There are not 8 units here. But can you imagine using Legos with a child or the equivalent thereof? And what you would do is what? You'd break one of those longs apart. Agreed? So we're going to do that visually. So this image right here will be equivalent to the next one that I'm going to draw. And it's going to have only 2 longs in it. And we're going to physically break apart one of those longs into how many units? 10. So here's 1, 2, 3, 4. It's not going to be perfect because I didn't get them drawn all the right size. 5, 6, 7, 8, 9, 10. Okay, so there's our picture of 10 units. It's not real convincing, but pretend. And then I need how many more units? 4, because they were there to begin with, right? So these are my original 4. So now from this picture, what I want to do is I want to remove 18. 18 would be 1 long. So in some sense, you're going to take this long and you're going to bring it out of the circle. And I need to remove 8 units. So I need to remove 8 of these, whichever 8 you want. And if I remove 8 of them, how many am I going to be left with? 6. So how many longs am I left with? 1. And units are 6. And counting up pretty quickly, we get 16. Okay, standard algorithm, again, the one you know and love, should again use the words regrouping, and you see that more in current curriculums. But what is the words that you remember using when you did this? Borrowing. Do you guys remember the word borrowing? That's the one I remember using too. So what we mysteriously did, and it is a little bit weird, is that we took the 3 and we marked it out and we wrote a 2. And not only that, but we took the 4 and we made it into a 14, which should totally not be allowed because I put a 2-digit number in a 1-digit spot. Right? I mean, like, that's really what it looks like. I just took something, and not only that, I took a 1 and I turned it into 10. I mean, like, that's a little bit weird. It should require some explanation as to why that's allowed. And of course, you and I both know why, but does the 6-year-old know why? Probably not. It looks a little bit like magic. And if you think that might look a little bit like magic, boy, you just wait till we get to multiplication. There's loads of magic going on there. Okay? It looks a little bit mysterious. So it should require a lot of, not a lot, but at least some explanation as to what we're actually doing. And what we are actually doing in terms of the blocks is we're taking that long and we're breaking it apart into 10 units. And I already had the 4, so the 4 plus the 10 that I already have is 14 units. That's why I'm writing a 14 down in the 1s column now. Of course, the explanation gets lost somewhere in the mix there, and when we subtract, we get the 16 that we were expecting, but it may or may not actually have meaning to the child that did it. Hopefully in your explanations and your use of concrete manipulatives, things like that, there is meaning attached to it. but there might not be. Now the expanded algorithm, excuse me, again, is a kind of a combination of these two ideas. In taking the 34 and breaking it into three, well, I'll write it out the way first way I did before, 30 plus 4, and then the 18 into 10 plus 8. Now you do have to recognize that you are subtracting, so the problem when I subtract is I can't do 4 minus 8. Okay? 30 minus 10 is totally fine. But the borrowing looks a little bit more obvious here because the 30 can actually become a 20, which means I really am borrowing 10. So the 4 becomes a 14. So it's sort of just like the shift. I'm taking 10 away from the 30 and I'm putting the 10 with the 4. It's much more obvious of why that's legit. Okay? And then the subtraction, of course, becomes the same subtraction as you did before. This is 10 and this is 6 for a total of 16. If you want to do it with the times 10s, you can do that too. So this is 3 times 10 plus 1 times 4. I need to subtract 1 times 10 and the 1 times 8. Of course, I don't have enough, so when I take the 3 and make it a 2 here, I'm taking away a 10 because it says times 10. And then I'm adding it over here. So, oops, not the 1, sorry. Oh, I wrote those sort of backwards, but I'm adding it to the 4 here, so this becomes a 14, you know, because I took away a 10. And of course, then I'm able to actually do the subtraction to give me 1 times 10 and 6 times 1. Pardon my ordering on those, but, and then I have my 16. Like I said, I'm a fan of the first piece of doing this, but both are actually considered the expanded algorithm.
Wouldn't your add the 1 times 10 plus 6 times 1?
Oh, yes, it is addition at this point. I'm sorry. Yes, let me fix that. Thank you. Yep, good point. Okay, there is one more subtraction algorithm, and this one is very interesting. Okay, this one is called equal additions, which sounds kind of funny because it's a subtraction algorithm with the word addition in the middle of it. So your interest should already be piqued, and you should be going like, wow, that's different. Okay, here's what you need to write down next to this, the words you need to write down. The goal of this method is that there's no borrowing. The goal is no borrowing. Or you could say no regrouping if you want. Okay, so here's the idea. The idea is that if I stood up, I will. If I stand up, and one of you also stands up here beside me, and we wanted to know what the difference in our heights were. We were both flat-footed on the ground, you know, barefoot on the ground or whatever, sock-footed. And then we both put on 2-inch heels. The difference in our heights would not be any different than when we were both on the ground in flats, right? Because we both added 2-inch heels to our height. You can picture that, right? So that's what we're going to do to these numbers. We're going to say 834 minus 158. And of course, as I write this down, and I will write it in that vertical format, what I notice is that this 8 at the end is sort of causing me problems because 8 is bigger than 4. So what we're going to do is we're going to add a convenient number. I don't want you to add a random number because in general that's not a helpful process for a child. What convenient number would I want to add to 8 to make it the best thing it could be? 2. Why would 2 be the number I'd like to add to 8? Because it makes it into a 0. I love 0. Subtracting with 0 is wonderful. Y'all with me? But if I add 2, like my 2-inch heels, to the number 158, I also have to add 2 to the 834. So we're going to add 2 to both of them. Okay, so I did not promise you that this was efficient, did I? Okay, so efficiency this is not, okay, but it is effective. So this would be 836 now and 160. Now in the ones column, can I subtract the ones column without borrowing? Yes, I can. But what happens when you look at the tens column? You cannot. So we're going to repeat the process for the tens column just like we did for the ones column. What would I need to add to 4? I mean, I already gave the answer. Man, that's what happens. What would I need to add to 6 to get it to become that 0 that we're wanting? A 4. But because the 6 is in the tens column, it's not really 6, it's 60. So my 4 is not really 4, it's 40. So we're going to add 40 to the bottom number because it turns it into a 0 in the tens column. That's my goal. I really just love zeros. They're fantastic. And again, I add 40 to both of them. So 836 plus 40 becomes what? 876. And 160 plus 40 becomes 200. And then again, the goal was no borrowing. Can I now subtract this with no borrowing? Yes. And notice I also can subtract it with no borrowing, and I could go from left to right if I wanted to, because there's no borrowing, so it doesn't matter. So if you really wanted to move from left to right at this point, you could. So we've got a 6, we've got a 7, we've got a 6. The answer is 676. The most common mistakes students make on this is stopping one step short. They'll remember to add the 2, but then they get to the tens column and they still borrow. If you're borrowing in the middle of equal additions, you've forgotten the whole goal. The goal is no borrowing. Or they'll forget and they'll try to randomly add something. For example, if I add the number 3 to this at the very beginning, it would actually work sort of in effect. The number on top would be bigger than the number on bottom. But that's not really the whole deal. The whole deal is to make it simple. And the way of making it simple is turning things into zeros on the bottom, not just into any number that might sort of work without the borrowing. So it's kind of a twofold process. Does that make sense? All right.